Okay, we'll go ahead and start student presentation session number 2. So our next speaker is Coleman-Hull from Kansas Beta. And he will tell us about economic connectedness in Kansas.
Yeah, hello, my name is Coleman-Hull. I'm from Emporia State University in Kansas, and yeah, I'm presenting over economic connectedness, specifically in Kansas. So economic connectedness technically is defined as a measure to determine how well connected an area is based upon the economic status of individuals within the area. So kind of to break that down, if you look at somebody who is, an example would be like somebody with a wage salary of $100,000 per year. This metric would look at how well connected, if they're friends with somebody who would make $20,000 per year. So outside of their economic class. We aren't looking at individuals who are making the same wealth. They're in the same economic class as that individual, but we're looking at people who are outside of that. So that's a good discernment there. This data was collected from Facebook, from the data set that we took it from. And so the friends are determined by if they're Facebook friends. So this is kind of a demographic of what a map looks like in terms of economic connectedness. Once again, that low economic connectedness would mean that most of your friends are in the same economic class as you. So if you made $100,000, you would be friends with a lot of other people who made $100,000. And as you can see, there's a lot of red down here in the southeast. And then this is done on a county level. It's pretty easy to take it from an individual level to a county level. If you just look at the average of a bunch of individuals, you can kind of generalize it to a county standard. So you can see red marks around here, and then the blue would be on the other end of the spectrum. That would mean that you have a lot of friends who are outside of your economic class. So you probably wouldn't have a lot of friends who make $100,000 in your life, but you would have a lot of people who are outside of it. And then somewhere in the middle here is more of the yellow area, and that would be people, you have like a diverse group of friends. So it's somewhere in the middle there. As we can see, we're in New York, right? And they're pretty towards the middle, generally speaking, I would say. You get a lot of kind of middle ground, more yellow looking territory there. And then in Kansas, where I'm from, there is a lot of blue. So it's a high economic connectedness. The other thing that you should look at from this map is there are big, like pretty sizable differences between each region. So you can see the Southeast has a lot of red within it. As I mentioned earlier, the West and the Northeast, they're more middle. And then the Midwest, if you kind of look at this and classify it as a Midwest region, it's going to have higher economic connectedness generally. So it's important to note. The predictor variables that go into economic connectedness that we wanted to look at, we weren't assuming that they do, but we wanted to look at specific variables taken from the census report that looked into economic connectedness. The ones that they also measured in this study were cohesive clustering, volunteering rate, support ratio, and civic organizations. And the two that I kind of want to discern here that kind of seem similar are cohesive clustering and support ratio. The difference between those two is with cohesive clustering, you would start with a given person. So you'd start with one individual and you would look at two of their friends to see if they're connected. And then support ratio, you would start with two different individuals who are considered friends, and you would try to find a connected friend to them. So that's the difference between those two, if those aren't clear. Then we also looked at a census report of Kansas, specifically Kansas communities, Kansas counties. And we got a couple variables from those. We got median household income, median family income, percent white, households, and per capita income. And so the two that maybe aren't as straightforward here are median household income and median family income. So if you look at a household, sometimes you'll find individuals who are roommates, and they wouldn't be considered part of the person's family, the individual's family. And so that would be included in the median household income, but not in the median family income. And so if you think about like urban and rural areas, in urban areas, you're probably going to find a lot more households with roommates than you are in rural areas. So that's important to note as well. We also added percent white just to look at an interesting kind of correlation, see if there's anything that dealt with that. We thought it would be an interesting variable to look into. And so we included that from the census report taken in Kansas as well. It wasn't in our initial data set. So a statistical model of this, right? Statistical representation isn't going to be perfect. It's not like a perfect model that you're going to find in like proven mathematics. Statistics are a lot more. They're pretty practical math, and so we want to create a function based on the data taken from all of our variables, and then we have a little bit of an error just because it's not perfect, right? And so our error we wanted to make as normal as possible because that would be ideal for a statistical model. We want to make our error normal, and we want to create a function with our different variables as best we could to measure how significantly each variable impacted general economic connectedness of an area. So we looked at a scatter plot first. We looked at the kind of model of how each variable generally affected the others. And all you need to pay attention to are these outside factors, because those are going to be how each variable affects economic connectedness specifically. So as you can see here, we want to find like some sort of linear trend, which would mean that there's a general linear association between the two variables. And you can see that between percent white and economic connectedness, there's kind of like more of a linear trend there, just like looking at it generally. But then you look at EC and CC, which is cohesive clustering, and that's a lot more random. There's not really a linear trend there. It's decently clear that that's the case, but still want to model it because we don't know that just from looking at it. Yeah, so look at those. We wanted to make this a math. We didn't just want to look at demographics all day. We wanted to make it a math and look at linear and nonlinear models that would best fit the data that we had collected. So our methodology was basically taking a bunch of interaction terms as well as our initial 9 variables and seeing if we could create a model that best fit economic connectedness. So there's 36 total pairs of interactions we could do. Interaction is basically you take one variable and then you take another variable, you find the interaction between those two just by like multiplying those kind of statistics. And then that's an interaction, which there are 36 different combinations of those. So yeah, we looked at 45 total different variables with those interactions, and that included our 9 original as well. So the models we looked at were 30 reasonable models, and we used forward and backward stepwise functions to slowly eliminate variables that weren't considered significant by our studio and didn't impact economic connectedness as much as we wanted to. So our first model we tried, we did 3 models without interaction, and we included all 9 variables of our original model at first. Yeah, included those models and then basically put them through our studio and saw if we got like a good linear model from those variables. The first time we did it, it wasn't amazing, but it was still pretty good. Like obviously these impacted economic connectedness in a way. And so our standard error, SE, is we want that low. And so we want it as close to 0 as possible. We got a pretty low standard error. That's a good standard error. And then R squared, we want that as close to 1 as possible. We got that, it's pretty good R squared as well. BIC, we want low. And we got a low value there. It can go negative. That just looks at overfitting a model, basically. So if you add extra variables, you want to be able to take out any unnecessary variables from that model. That's what that looks at. And then there were major issues because those asterisks next to them, that means that those were insignificant variables. So we needed to take those out for various reasons because they didn't fit the methodology we wanted to see from the model. So we took out those insignificant models or variables, and we got it down to 4 different variables. We had SR, CO, MFI, and PW, which is support ratio, civic organizations, median family income, and percent white. And those were considered significant by our studio. And yeah, then our standard error, as you can see, dropped, which is amazing. Our adjusted R squared went up, good. And then BIC went down as well. And there weren't any insignificant variables, which is awesome. But just to check, we added on the next significant variable, what would be like the closest to being significant, which was HH, which is households. And we added that on into the model just to be sure that we were looking at a good model with our 4 significant variables there in model number two. So that created a standard error, which was actually lower, and an adjusted R squared, which is higher, which is good. But it did result in the BIC, which was not in the direction that we wanted it to go. So I think overall, the issue with this model is just that we added an insignificant variable, and we want a p-value to say that it's significant. We want a p-value of 0.05. We want it to be less than that. And HH was 0.2, which wasn't ideal. So I thought the best model without interaction was model number 2 from this slide. But then we added interaction. So interaction would cause the model to become less linear, but it also adds like a lot of interaction between each models, and we get like a wider variety of variables that we can look into just overall in our overall model. And so I didn't have enough space to add a 45 model on here, and I didn't really want to look at that, to be completely honest. And so we added 8 interaction pairs that were considered right off the bat pretty significant. Just eliminated some interactions that just didn't seem significant right off the bat. So we got a low standard error. If you remember, that standard error is lower than all of the other models on the last slide, and the adjusted R squared kind of skyrocketed up, which is great. The BIC though did go in the wrong direction. It's not exactly where we want it to be. And then we did have a lot of insignificant variables within the model. So those variables did not necessarily impact economic connectedness as much as we wanted it to. But when we eliminated these insignificant variables, we came up with this model. And that resulted in a standard error, which went a little bit up, and an adjusted R squared, which went a little bit down. But that just comes with removing variables. You just aren't going to have as great of a value on each of those areas. And then BIC went in the direction we wanted to. That's the best BIC we've seen so far. So yeah, MHI and MHI-MFI, that interaction pair, those are insignificant, as you can see by the asterisks, but they are very close to that p-value that we wanted of 0.05, and they made the model a lot better. So I went ahead and left those in. I thought it was a really good model. Just in general, we thought it was a really good model. So yeah, once again, going through that process, added CO into that equation, and then it just resulted in a worse model overall. So we left that one out, but we included that next significant variable. What would have been the next significant variable? So looking closer at these models, this is like the linear representation of our first 4-variable model that was best from that first slide. The big thing to note from this slide is that you see some of those are positive interactions. They have pluses in front of the numerical values. That just means if you have a higher, let's take CO, for example, if you have a higher CO, your economic connectedness is going to go up. And so SR, if that goes up, then economic connectedness is going to go down just because it has a negative in front of it. So that's important to note from this model and the next one I'm going to show you. This p-value, it should be 2.2 times e to the negative 16. That's very low compared to a very big p-value. That would not be good. But this one is a low p-value, so that's very good, which means that the model is the overall model is considered significant, as well as the individual variables within the model. Yeah, so these are kind of graphs that we can check as well within RStudio. We want this first model in the top left, we want that red line to be as horizontal as possible, which would mean that there's a lot of variance within the overall model itself. This isn't horizontal, it's just not, but it's relatively close. Like it's a good variance. And as you can see from this outlier and this outlier, those kind of modify the overall horizontality. I don't know if that's a word, but it just modifies it in a way that is impacted by this outlier and this outlier here. I think overall that's a good fit. And then normality, we want those points to be as close to that linear line, we want that model, those points to be as close to the line as possible. And it just looks really good. Same thing goes here with scale location. We want a horizontal line there. We don't get that, but outlier here clearly impacts that end of the data. And that's the big thing there. I think with this one, it's a relatively good model. And as we can see, there's this giant outlier point in the residuals versus leverage graph that clearly impacts the rest of the data. This one we're making sure that it's not below this -3 line or above this 3 line up here or above these dashed lines over here as well. So we're pretty good over there. Our interaction model, which I considered to be the best model within the 6 that we looked at during this presentation. It's just, it's a solid model. And as you can see, look for those pluses and minuses within that, that overall equation. Yeah, you can see positive and negative correlation. And then a p-value of 2.2 times e to the -16 is amazing. And then predictor variables, MHI and MFI and MHI, as I talked about earlier, those were deemed insignificant, which is maybe the only big issue with this model. So major improvements, I think, in terms of the graph, you see a lot more horizontal of a line in this top left one. Normal QQ is still really good. The data is normal. And then we have a pretty horizontal line there as well. Just this one outlier point that's kind of affecting the data in that 4th graph. So our conclusion, VR, which is volunteering rate and per capita income, PCI, were not included in our final model, which could tell us that those variables just overall aren't very significant in affecting economic connectedness. And then median family income and percent white were the most important variables, meaning that they had like a high positive correlation with economic connectedness, which is good. As those go up, economic connectedness will go up. But then two questions that came from this this data set is Facebook a good source for the data? Is that how we want to look at friendships, or do we want to determine that from another perspective? And then can we extend it to the Midwest region? There was a lot of blue within the Midwest region. I thought it was decently clear that the Midwest was pretty distinct from other regions in the United States. But can it be extended to the Midwest region? So yeah, I think that's the presentation. And here are references. Okay.
But like it's sometimes one or two questions.
Yeah. The scatter, can you repeat that one more time? Scatter plot rate. Yeah. Go back to that. Mhm.
We can say that there's
Yeah. Yeah, so that would have, that's why that interaction was pretty significant later on, because there is like that linear trend within those models that shows like linear correlation between those.
and how are going to basically they came by order to have said that this county is really that's different.
And Mike. If Mike was going on, what did you want to try? What did you want to like? Why did you try to use a quadratic?
Yeah. From the outside of these scatter plots, there isn't a lot of like non-linear trends. And so that would make it to be where like you would want to square variables, is basically what you would be doing there. And that's kind of why we didn't look at those as much, just because there isn't in the scatter plots kind of that non-linear exponential association. Yeah.
So, did you say that you used data from Facebook and census data?
We use census data, which they define friends based on Facebook friends.
Also, that's how you're able to.
Yes.
Right? 'Cause-
Yes. I think so.
Okay, so is this a point, so this would be like a point in time, right? So, like, the idea of economic openness, can it be tracked across time?
We could track it across time if we looked at like Facebook friends over time, I suppose.
But if you did, you were able to, because I'm trying to understand the application of this. So now that you understand, economic, I got it. Okay, so what would you like to do with it?
I think like generalizing it to like the Midwest region or even like Kansas, like if you look at how diverse like a friend group is, or how unique, it just determines how well you are connected with like friends who are outside of your wage gap or wage group, your economic class. And you would want to ideally get a pretty diverse friend group, I think. And we like can kind of look at that through like where each region could maybe like get a more diverse friend group compared to their like economic class. Makes sense.
Let's thank our speaker.